Hello, everyone. So last time we did basically strong induction and the chapter 5, which was about induction and recursion. So we skipped few parts though of that chapter. So for the exam, always the reference will be the materials covered in the class and the lecture notes. So that's the main reference, and of course the assignments as well. So these are the main two references, the lecture notes and the assignments. And then after studying these two notes and these two resources, you can work on other resources such as the textbook and the additional assignments on the textbook and other resources for these topics. So today we want to start chapter 6. Which is about counting, combinatorics, and counting problems, or what your book says is counting. And 6.1 is about the basics of counting. So we want to start with the product rule. The product rule. Suppose that, well, this product rule, by the way, is not related to the product rule that you learn in calculus, which is about the derivative of product of two functions. So this one also called product rule, or sometimes this is called MN rule, but it's unrelated to the product rule you learn in calculus. So suppose that task 1 can be performed in, let's say, N1 ways, and task 2 can be performed, let's say, in N2 ways. Then there are N1 times N2 ways to perform task 1 and task 2 together. Okay, so for example, let me give you an example. Let's say, suppose that we have 3 options for lunch and 4 options for dinner in a specific day. In total, how many options do we have for our meal in that day? So 3 options for lunch, 4 options for dinner. How many options in total for lunch and dinner? Well, some people here think that in total we have 7 options because 3 options for lunch, 4 options for dinner. But that's not true. In total, if we have for task 1 and 1 options, task 2 and 2 options, then in total for performing task 1 and 2 together, we have N1 times N2 options. So 3 options for lunch, 4 options for dinner. Then for the meal, which means lunch plus dinner, and then we have 3 times 4, which is 12 options. So let me explain about this. Let's see why we have, so according to the product rule, we have 3 times 4 equals 12 options for the meal. By meal, we mean lunch plus dinner. For that day. This can be verified as follows. See, we can verify. So I'm claiming that I have 12. We have 12 options in total, but we can also verify this. How can we verify? So see, we have three options for lunch. So we can see, let's say we have lunch 1, lunch 2, lunch 3. And then we have 4 options for dinner. So dinner 1, dinner 2, dinner 3, and dinner 4. Then for the meal, lunch plus dinner. Then what are my options? So I can choose lunch 1 with dinner 1. So lunch 1 is one specific food, could be, for example, chicken pizza, for example. Or lunch 2 could be some other food, lunch 3, some other food, and dinner 1, let's say, is a specific salad, for example, and so on. So in total, I can choose, let's say, lunch 1 with dinner 1. What else can I choose? I can choose, let's say, lunch 1 with dinner 2, right? Lunch 1, dinner 3, lunch 1, dinner 4. So this is already 4 options, and I'm just choosing lunch 1 for these 4 options. Then similarly, I can choose, I have another 4 options with lunch 2, right? So I can say lunch 2 and dinner 1, lunch 2 and dinner 4. And then all the way to lunch 3. So let's say here, lunch 3, dinner 1, all the way to lunch 3, dinner 4. So total 12 options. See, with lunch 1, I have 4 options. Dinner 1, dinner 2, dinner 3, dinner 4. With lunch 2, 4 options. Lunch 3, 4 options. And therefore total 12 options. Okay, now one generalization for this product rule is that, let's say, if you have k tasks and you want to perform task 1, task 2 to task k, so suppose that, let's say, a procedure includes performing k tasks. Task 1 can be performed in, let's say, n1 ways, and all the way to task k can be performed in nk ways. Then to complete this procedure, we have n1 times n2 times nk options. Have k tasks, and so it's the generalization of the previous one. Previous version, we said we have 2 tasks and 1 ways for the first task and 2 ways for the second task. In total, we have n1 times n2 ways or options. Say ways because I said ways previously. Here we have the k tasks. So task 1 in 1 ways, task 2 in 2 ways, and all the way to task k in k ways. Then in total, we have n1 times n2 all the way times nk ways to complete this procedure and perform all these tasks together. So again, similar example, we can do this time. Suppose that a meal consists of breakfast with 4 options, lunch with 3 options, and let's say dinner again with 3 options. In total, we have how many options for our meal? So 4 options for the breakfast, 3 options for the lunch, 3 options for the dinner. So that's going to be 36 options for the meal. So 3 tasks in this, or 3 tasks: breakfast, lunch, dinner. And first one has 4 options, second 3 options, third 3 options. In total, we will have 4 times 3 times 3 options for the meal for that, let's say, specific day. Okay, another example. Let's say suppose that we have a class of 14 students. We want to choose a committee of 2 people, of 2 students, for a specific conference. The first person will be an organizer. And second person will be, let's say, the assistant. So in total, how many, in how many ways can we choose our committee? Okay, so we have a class with student 1 all the way to student 14. And we want to choose a committee of 2 people. So we will have 2 people, 2 role here. So here we will have organizer. And here we will have assistant. So how many options do I have? So for the organizer, how many options do I have? So I can choose any of the 14 students. So 14 options here. 14 options for the organizer. Now for the assistant, how many options do I have? So let's say, for example, for organizer, I can choose student 1, student 2, all the way to student 14. So let's say, for example, I choose student 1 for the organizer. Then for assistant, I cannot choose student 1 again, right? Because student 1 has been already chosen as an organizer. So for assistant, how many options do I have now? Am I left with? So I'll be left with 13 options because student 1 has been already chosen. So 13 students are remaining. So then for assistant, I will have 13 options because 1 student has been already chosen for as an organizer, and I cannot choose that student again. So whether the organizer is student 1, or it could be student 2, or student 3, and so on. But regardless of which student has been chosen as an organizer, that student cannot be chosen again to be the assistant. So I will be left with 13, which is 14 minus 1 options for the assistant, since the assistant cannot be the same student as the organizer. So in total, we will have 14 times 13 ways to choose this committee. Okay, so 14 times 13 ways to choose this committee. Okay, one remark here that I can mention is that, the product rule can be expressed using set theory notation as follows. So we can say that the cardinality of, let's say, A1 times A2 times AK is equal to cardinality of A1 times cardinality A2 times cardinality AK. So here, where A1 cross A2 cross AK is the set of all K tuples, let's say A1 to AK, such that A1 belongs to A1 all the way to AK belongs to AK. So this is still same as a product rule. Let me explain about this. Let's look at one of the examples we did. For example, let's say the one with the meal, for example, here. This one, we had two tasks. So we had a set of elements for lunch and set of elements for dinner. So in our notation, let's say you can call them capital A1 and capital A2. Let's say if capital A1 is the set of all lunches that you have, lunch 1, lunch 2, lunch 3. And capital A2 is the set of all dinners that you have, dinner 1, dinner 2, dinner 3, dinner 4. Then A1 cross A2 means lunch and dinner, right? So A1 cross A2 means, when we talk about the whole meal, that means we talk about lunch and dinner. So one way to express it is using pairs, right? So we can say lunch 1, comma, dinner 1, and then lunch 1, comma, dinner 2, and lunch 1, dinner 3, and all the way to lunch 3, dinner 4. So we can use pairs. So the set of all these pairs is called A1 cross A2, the Cartesian product of A1 and A2. And the question was, how many of such pairs we have, right? And the answer was the number of elements in A1, which means number of lunches, times number of elements in A2, which means number of dinners. So my point is, we can express this with set theory. We just need to call that set of lunches as, let's say, A1, set of dinners A2, and then the set of meals would be the set of elements in A1 cross A2, because each meal corresponds to one pair, and each pair means one element of A1 cross A2, A1 Cartesian product with A2. So if you want to count the number of meals, that means you have to count the number of elements in A1 cross A2, which by product rule or MN rule is given by number of elements in A1 times number of elements in A2. So number of lunches times number of dinners. And then we said it's 3 times 4 or 12. So in general, if we have, let's say, K tasks, for task 1, you can consider A1, the set of all ways that you can perform A1. For A2, you can put the ways that you can perform the task to call the set of all these ways A2, and all the way to AK. And then to complete the whole procedure, that means you have to look at the number of elements in A1 cross A2 cross all the way to AK. And that can be found by multiplying number of elements in A1 and number of elements in A2 all the way to number of elements in AK. So this is the MN rule, but with set theory notation. Okay, now let's look at another example. So let A be a set with n elements. Show that the number of subsets of A is given by 2 to power n. Number of subsets of a set with n elements is 2 to power n. Well, how can we prove this proof? Each subset, let's say S of A, corresponds to, so let's first of all choose a notation for A. So let's say A equals A1 to AN. Each subset S of A corresponds to filling of the following n squares, each with 0 if AI does not belong to S, or 1 if AI belongs to S. So let's consider n squares. See, 1, 2, 3, and n. So for the first square, each of these squares, I'm going to fill them with either 0 or 1. Now, how can I decide whether 0 or 1? So I have to look at my S. Let's say I have an arbitrary subset of A, I'm calling it S. First, look at S. Does S contain A1? If yes, then put 1 here. So 1 if A1 belongs to S, and 0 if A1 does not belong to S. Similarly, this one, again, 1 if A2 belongs to S, and 0 if A2 does not belong to S. And all the way to the last one, 1 if AN belongs to S, 0 if AN does not belong to S. So let me give you an example. Let's say, for example, if A equals 1, 2, 3, 8, 9, and S equals, let's say, 3, 8, then S corresponds to so see, if let's say A is 1, 2, 3, 8, 9, how many elements A has? A has 5 elements, so I have to draw 5 squares. And each of these 5 squares is going to be filled with either 0 or 1. How do I decide? For the first square, I have to look. The first element of A is 1. Is 1 in S? No, so I have to fill it with 0. What about the second square? Second element of A is 2. Is 2 in S? No, so I have to fill it with 0 again. Third element of A is 3. Is 3 is in S? Yes, so I have to fill it with 1. Next element is 8. Is 8 in S? Yes, so again, fill it with 1. Next element, 9. Is 9 in S? Answer is no, so fill it with 0. So then S corresponds to 0, 0, 1, 1, 0. So each subset of S, each subset of A corresponds to 1 and exactly 1 sequence of zeros and ones, where ith element is 0 if AI is not in S, and ith element is 1 if AI is in S. So how many options do I have now in total to fill these squares with 0 and 1? So for first square, now the first square can be filled with 2 numbers, right? Which is either 0 or 1. Again, similarly, the second square can be filled with 2 numbers, which is 0 or 1. And all the way to nth square can be filled with, again, 2 numbers. So in total, we can fill the above n squares in 2 times 2 times 2 equals 2 to power n ways. This means A has 2 to power n subsets. Okay, it seems that the square is free and the screen is free. So let me stop share. Share again. Okay. Yeah, each of the squares can be filled with 2 elements. So in total, we have 2 times 2 times 2, 2 to power n ways. And therefore, A has 2 to power n subsets. So let me give you one remark here. So for example, empty set is a subset of every set. So if you have empty set will correspond to which sequence of zeros and ones? Empty set, if you have empty set, that means no element is in your S. If S is empty set, then no element will be in S. So all the squares will be filled with zeros. In the other extreme case, if S is the whole A, is A itself, then that means S contains all AIs. And therefore, in that case, S equals A will correspond to the sequence where it contains the sequence of all ones. All n elements will be ones. So these are two extreme cases, and the other cases we will have bunch of zeros and bunch of ones. So each of these squares can be filled with 2 options. So in total, we have 2 times 2 times 2 times 2 equals 2 to power n options. So let me give you an example. Let's say if A equals, for example, 1 and 3, then A has how many subsets? A has 2 elements, so A has 2 to power 2 subsets, which means 4. And what are those 4? Empty set, 1, 3, and 1 and 3. So 4 subsets. Okay, another example. Let A equals, let's say 1, 3, 8, and B equals 2, 4, 10, 12. How many? So let's say part A. How many functions exist with domain A and range or let's say with domain A and codomain B. Part B, how many one-to-one functions exist with domain A and codomain B. So for functions, so see, what does a function do? Function, assigns exactly one output to each input. So look at the first input. the domain is supposed to be A, so we are supposed to have 3 inputs. So for the first input, how many options do we have to assign as an output? So part A, I charge the pencil. Part A. So the first input is x equals 1. We can assign how many outputs, how many options do we have to assign as an output any element of B, because B is supposed to be codomain, so the outputs are supposed to be chosen from B. So we have 4 options. We can we have, say we have 4 options. To assign as to assign an output to this input, right? Or this input. And the second input, x equals 3. Again, we have 4 options, right? Because in part A, we are it's not required to be a one-to-one function. Therefore, if, for example, if to the first input, let's say we assign 2 as an output, then for the second input, we can again use 2. There is no problem. If you do not have to have a one-to-one function, if any function is acceptable for you, then it's okay to have, let's say, 2 occurring as an output twice. So you still have a function. You will not have a function if you assign 2 outputs to 1 input. For example, let's say if I assign 2 and 4, both of them as an output to 1, then I will not have a function. Because in order to have a function, each input must have exactly 1 output. So the first input is 1, and 1 must have exactly 1 output, either 2 or 4 or 10 or 12. Any of them are okay, but not 2 of them at the same time. Okay, so if I assign, for example, 2 and 4, both of them as outputs to 1, then that's not okay. Then I will not have a function. But as long as I assign exactly 1 output to each input, then I will have a function. So for the first input, which is 1, I have 4 options to assign as an output, either 2 or 4 or 10 or 12, one of these numbers. Then for the second input, again, I have 4 options, either 2 or 4 or 10 or 12. Like I said, even if 2 has been already used for the first input, it's okay to use it as for the second input as well, because it's not required to have a one-to-one function. If you want to have a one-to-one function and 2 has been already used, then you cannot choose 2 anymore. But if you do not have to have a one-to-one function, you just want to have a function, 2 has been chosen once, you can also choose it as a second time, even as a third time, that's okay. So the first input, we have 4 options to assign an example for this input. Again, for the second input, same thing, 4 options. For the third input, which is x equals 8. Again, we have 4 options to assign as an output. So in total, how many options do we have? In total, we have 4 times 4 times 4 equals 64 ways to define a function f, let's say, with domain A and codomain B. We know that the mathematical notation to write a function with domain A and codomain B is to write f from A to B. This means A is the domain and B is the codomain. So we have 3 inputs. For each of those three inputs, we have 4 options. So in total, we have 4 times 4 times 4, or 4 to the power 3, or 64 ways to define a function f from A to B. Now, part B. Again, let's see how we can do part B again for the first input. For the first input, which we said it's x equals 1. Again, we have 4 options, right? To assign as an output, to assign an output for this input. For the second number, or for the second input, x equals 3. How many options do we have? See, for the first input, one number has been already chosen as an output. Let's say if 2 has been already chosen as an output of the first input, which is 1. Then for the second input, I cannot choose 2 anymore, because for one-to-one function, you are not allowed to have a repeated output. So if 2 has been already appeared as an output once, it's not allowed to be appear as an output for the second time. So if 2 has been already used, then for the second input, you cannot choose 2 anymore, and then you will be left with 3 options. Okay, so for the first input, we still have 4 options for a one-to-one function. But for the second input, we have now 3 options, because one option or one number has been already chosen as an output of the first input. So for the second number, for the second input, which is x equals 3, we have 4 minus 1 options to assign as an output, since we are not allowed to have a repeated output, since a one-to-one function is not allowed to have a repeated output. And finally, for the third input, which is x equals 8, how many options do I have to assign as an output? We have, for this input, we have, see, one number has been already chosen for the first input. One number has been chosen for the second input. See, I have to choose from this list, right? One of these numbers has been chosen for the first input. One of these numbers has been chosen for the second input. So 2 of them has been already gone. Two of them have been gone. And I'm left with 4 minus 2, which is 2, options to assign as an output of the third input. So we have 4 minus 2. It's 2 options to assign. Yes. 2 of outputs have been used for the previous 2 inputs. So in total, how many? Let's say by the product rule, we have how many options to define our one-to-one function? One-to-one function means a function with no repeated output. We have 4 times 3 times 2 equals 24 ways to define a one-to-one function. F with domain A and codomain B. The number of one-to-one functions is, of course, less than total number of functions. Total number of functions was 64 with domain A, codomain B. But for one-to-one functions with domain A, codomain B, the number is only 24. The number of one-to-one functions with domain A and codomain B is 24.